Of course, we see that after that first dark spot, we do in fact see another bright line. That new bright line needs to be explained, and the dark line. Well, after we get further than this angle, these won't be perfectly canceling out anymore, and that's how we get the new bright line. But as far as the next dark line, how would we understand that? Well, we can split this, instead of into 2 halves, we can split it into 4 quarters, and compare not from this ray to the ray that begins half of the width away, just compare it to the ray that begins a quarter of the width away. In that case, the path length difference, as we see here, is only a over 4 sine theta. So we'll get a minimum whenever a over 4 sine theta equals lambda over 2. That will require a larger value of theta, so that the sine of theta is twice as much. That means that a sine theta is equal to 2 lambda. In fact, we can always break this this line here, this opening, into 2m different segments. Then the phase difference between the top of a segment and the top of the next segment will simply be a over 2m, where m is any integer, times the sine of theta, and that will have to equal lambda over 2. The 2's will cancel, and if we put this together, we find that any time a sine theta equals m lambda, where m is any non-zero positive integer, actually it can be a negative integer, but it can't be 0. Anytime a sine theta equals m lambda, we will get a minimum for the single slit. In other words, we will get a dark fringe. What this tells us is that a single slit diffraction experiment will give us dark fringes where the path length difference, a sine theta, between the top and the bottom are integer multiples of a wavelength. You might expect this to give you positive or bright fringes, but the key is, if there's an integer number of wavelengths between the top and the bottom, the path length difference for the top and the bottom, then in between there are enough other pairings that cancel out that we will get a 0 amplitude over on this side.